Today we're going to learn chapter 4, operational amplifiers, part 1. So the course objective is to model, analyze, design operational amplifiers. The module objective is to model the opamp device and also some fundamental opamp circuits. So the first question that you might have is, what is opamp? So by its name, it's called operational amplifiers. It amplifies signal when the signal is too small and you want to amplify the signal so that it can be read by the microcontrollers or computer. In that case, you will need amplifiers. So this is one amplifier. This is made by Texas Instruments. Its model is me2040. So if you open the data sheet of this chip, inside of the document you will see a pin layout. It tells you what are these pins. And if we look more into the details, we see that these are given in 4 different groups. The first group contains the 3 pins. This is input and this is the output. And within these 3 pins attached to the first group. And these 4 different groups, they are identical. So we have 4 opamps in this circuit. And each opamp has 3 pins. There are 2 inputs and 1 output. There are 4 groups. And they share the power. This is VCC and this is VEE or ground. Let's take one group out and we look into one set of opamp. 2 input, one is called in plus and the other one is in minus. So it's also here. So in plus, in minus. So I'm looking at the first group right now. And the output is over here, the in out. And the VCC and the VEE, they are shared. So I'm taking VCC and VEE out. So VCC is connected to the power and VEE connected to the negative side of the power. So in this setup, if the voltage for this battery pack that is 5 volts and the other side, if they are identical, the other side will be negative 5 volts because the reference is given here. So it means that we apply the 5 volts on VCC and VEE that is negative 5 volts. So it means that the maximum output for this opamp is 5 volts. The minimum output for this opamp that is negative 5 volts in that setup. For this chip, there is also a different setup. You can connect VEE to the ground. And similarly, if we use a VCC at 5 volts, it means that we connect VCC to 5 volts and a VEE, that will be the ground. So the output range for this setup that is between 0 and 5 volts. So the next topic is a model of the opamp device. So this is the opamp that we take from the previous page. And how do you model this? This is a linear model of opamp. So let's find their pins first. So the output is over here. So this is one pin from the opamp is over here, right? The same thing on this side. I didn't draw that. And the input pins are here. One is here and the other one is here. This is the in plus, and this is the in minus. So this is in minus. The difference between the two that is represented by the voltage difference V in. So V in that is equal to, if we call this side V plus and this side V minus, this will be V plus minus V minus. So that is called V in. And this linear model models the amplification by using a dependent source. The source output on this side right over here, that is a coefficient AO times V in. So we know that the output from here, that is always AO times the signal difference between V in and V minus. And of course, for any circuits, it will come with some companion resistance, right? So the same thing. For the input end, we model it as a one resistor between the in plus and in minus terminals. Between the output of this dependent source and the output that you're going to use to drive any other additional loads, there is a one resistor. The resistor have a value of RO. The RI is the input resistance, and the RO that is output resistance. The concept of linear model, it models the opamp as a voltage dependent source. The input signal will be either connected to the plus sign or connected to the minus sign, or you have 2 signals connected to both. What is the ideal opamp model? The ideal opamp model has 3 assumptions. The first assumption is RO is equal to 0. Because this opamp is going to amplify signals in a typical setup. And if RO is too big, it means that if we apply to another load here, And this RO will consume a lot of electricity, right? That's not something that we want. We want all the electricity to be used on the external load. So this is why we want RO to be very small. So that is also the case for typical op-amps. In typical op-amps, RO is very small. It's only a few ohms. We want Ri to be very large. So if Ri that is very large, so it means the current will be very small through the circuit. It means that we won't consume too much power from the signal input. And the AO, we want it to be super large. So in the ideal case, we assume the amplification gain is equal to infinity. If we look at RO that is equal to 0, assume that this resistor is 0, and what this output will be. So the output will be equal to AO times V in, right? So V in, that is the difference between the V plus and V minus. So we call this node have a voltage of V plus, and the other negative node we call it V minus. So we can get a VO that is equal to A times V plus minus V minus, right? So that is the conclusion that we can get from the first assumption. The second, Ri is equal to infinity. When this Ri is infinity, what does it mean? Like the infinity means that it's open. There's no current going through this resistor anymore. Because the resistance is too large, there's barely any current going through it. So we know that I plus is equal to I minus equal to 0. I plus is the current goes into the non-inverting terminal. This terminal is the inverting terminal. And the output here is the amplification gain times the same sign of a V plus and a negative sign of a V minus. Assumption A that is equal to infinity. When A is equal to infinity, the output becomes infinity number times the difference. So that is the conclusion that we get. For ideal op-amp model, I plus is equal to I minus is equal to 0, and V plus is equal to V minus. So this picture shows the transfer plots for some commercial op-amps. The first line, red, is over here, is LM324. If you connect it to the power source of plus minus 15 volts, the maximum range of the output is negative 15 to, this should be 15 volts. And for the second op-amp, LMC6492, is given in this plot. And it has a power supply of a plus minus 5 volts, and the output will be within the range of negative 5 volts and 5 volts. And similarly for the third op-amp, between negative 1.5 volts and 1.5 volts. This is what you see from the response. And you see there is a range. Within this range, it's a linear. So this is called a linear region. Beyond that area, if you keep increasing V in, it will be kept at some value that is decided by the power supply for the op-amp. You cannot go beyond the power supply, right? So this tells us the relationship between the input voltage V in and the output voltage VO. So by knowing the linear region and the saturation region, if I give you the plot of this, and you will be able to identify the saturation region. So look at this plot. We have the input following this triangular shape signal, and the output at the beginning is linearly related to that, and it's come to until the input is about 1. When the input is about 1, and the output will become negative 4, and it's kept at negative 4. We'll be able to identify the saturation region is negative 4 over there. And given this plot, you can also roughly calculate the amplification gain. The amplification gain will be the ratio between the output and the input. So this is the first application for op-amp device called a unit gain buffer. So we have an op-amp over here, and this is the power supply. We don't need to worry too much about the power supply. And the one signal that is connected to the non-inverting terminal, and the output is over here. And there is one wire that is connected between the output and the inverting terminal. So this setup is called a unit gain buffer. And then we want to know why this is called a unit gain buffer. So let's do some circuit analysis. So we're going to replace this op-amp by using its linear model. I replace this by using one input resistor, one output resistor, and one dependent power source. So the input V in here, between V plus and V minus, there is one resistor, we call it Ri, This is the output side. It has one resistor and one dependent source. At the same time, because we add one wire from the output to the inverting terminal, we are going to do the same thing. We add one wire from the output. This is the output, right? And I connect it to the inverting terminal V minus. So this is how we get the circuit. Now you know how we can use the linear model for analysis. We just replace that and draw the rest of the circuit. Now if we look at this circuit again, so this is a single loop circuit. For this single loop circuit, to find the relationship between output VO and the signal VS, we'll be able to use loop analysis. We write a KVL equation for that. So if we write a KVL equation for this single loop, we'll have a negative VS plus V in, that is the voltage drop. Then there's another voltage drop on this RO. If we use the current I, that will be RO times this current I as the mesh current, plus AO times V in. So that is how we find the KVL equation. And we have a dependent source over here. We need an additional equation. V in is over here. We'll write a V in terms of the loop current, which is I times Ri. By having the two equations, we'll be able to solve the output VO. So we find the relationship between VO and VS is in this expression. And if we assume this is the ideal opamp model, in ideal opamp model Ri, that is the infinity, and this RO is equal to 0, and AO is infinity times infinity, this is infinity, this is 0. So this tells us that this term goes to 0. So with the ideal opamp model, we find a 1 divided by 1 plus 0, that is equal to 1. It tells us that the output is always equal to the input. So this is why it's called a unit gain buffer. By doing this setup, the output is equal to the input. And we can verify the accuracy of an ideal opamp model by applying the typical values. Say Ri, that is equal to 10 to the power of 8, RO is equal to 10 ohm, AO is equal to 10 to the power of 16. We plug this value in there, and we get a number that is very, very close to 1. You might want to know, why do we do the unit buffer? The output is always equal to the input. What's the point of using this setup? Why don't we just connect the source directly to the load? Why do we want to put something else in between? So this comes to the application of voltage follower. Why do we need to connect the output to the inverting terminal to separate the signal? So let's compare the two cases. The first case, we connect the signal directly to the resistor network. And the second case is that we put an opamp in between and I connect it to the same resistive network. For the first setup, if we calculate a VO, the voltage applied on the resistor network, we know that it will be equal to Vs minus the voltage drop on this resistor Rs. So VO that equal to Vs minus Ra times Rs. And in the second case, VO is always equal to Vs. If we want the voltage controlled by the signal applied on the resistor network, it's better to have this unit buffer set up. And at the same time, another main difference between these two setups is that the setup with the opamp, the source supplies no power. This signal source supplies no power, and the power that is supplied by the external power supply connected with this opamp. So you have a VCC on the top, and on the other side you can either have VEE or ground. It depends on which opamp you use. You can find all those details from the datasheet of any opamps. So the voltage follower, it isolates one circuit from another. It's especially useful if the source has a little power. So the second setup is a typical setup. It's application 2, amplification. This is a typical setup for amplification. We have a signal connected to the inverting terminal, and the non-inverting terminal is connected to the ground. And we have an input signal connected with one resistor R1. Between the output and the input, we connected with one resistor R2. Let's find a relationship between VO and VS. So we are going to use ideal opamp model because it's great to simplify the calculation and also it's accurate enough. We have this relationship, V plus is equal to V minus, and I minus is equal to I plus, that is equal to 0. So these two currents are 0. And at the same time, V plus is equal to V minus. The node voltages are 0. So we'll apply KCL at the inverting terminal. Because the non-inverting terminal is simply 0, it connects to the reference. So we know that V plus is equal to 0. And V minus in that case is also equal to 0 because V minus is equal to V plus. And we apply KCL at a V minus node. This node have a nodal voltage of Vs, right? Because this is the reference. This is Vs minus V minus divided by R1 plus the current goes into this node from this branch. This node have a nodal voltage of VO and this node a nodal voltage of V minus. So VO minus V minus divided by R2, that is equal to 0. So this is the equation that we have. And from this equation, we will be able to find the gain. VO over Vs, that is equal to negative R2 over R1. So now you can see that through selecting different resistors, you will be able to adjust the gain. If you want to amplify your signal by 5 times, you just need to select R2 that is equal to 5 times over R1. And what if we use a linear model instead of the ideal op-amp model? And the ideal model is pretty straightforward, but I want to make my result more accurate. In that case, you can use a linear model. So if we set up a linear model, we replace this op-amp by using this circuit. So that is what we're going to do. So this is a linear model with one resistor on the upper side and a dependent source, and this input resistor Ri. So we put this back into the circuit, and this will be what I have. You might say this circuit is not very easy to read. We can move these things around and make the circuit easier to read. Move this outside a little bit, and then move this inside a little bit. This is the circuit that we have, right? So if I give you a circuit like this, you will be able to find anything from the circuit. So you can use the nodal analysis to find the VO in terms of Vs. So if we do a nodal analysis, in this problem we have two nodes. One is V1, the other one is VO. So you set up the equation. Because we have a dependent source, it means that we have another equation from the controlling variable. The controlling variable is VE. So the VE is equal to negative V1, right? V1 is the voltage between this node and the reference node. So VE is equal to negative V1. And we put all these together, we can solve the equation that give us the ratio of VO over Vs. So now comparing the ideal op-amp model and the linear model, you see the difference in derivation. So the ideal op-amp model is always much easier to deal with. And if we assign the typical values to the linear model, we'll be able to find the gain is roughly the same as the one that we find from the ideal op-amp model, almost the same. The third application is a differential amplifier. So just now we showed you how to amplify one signal. So now if we want to amplify the difference between two signals, so this is the setup that we're going to use. So one signal that will connect to the inverting terminal, the other signal will be connected to the non-inverting terminal. And at the same time we have different resistors connected there and the resistor connected here. Then we want to see what's the result if we have this setup. Again, we're going to use the ideal op-amp model for analysis. So ideal op-amp model tells us that the current goes into the two terminals are zeros, and the nodal voltage at the two terminals, they are the same. Something you need to pay attention is that they are not zero. They don't have to be zeros. So these are the conclusions that we have from ideal op-amp model. And then the rest is the same as what we did in chapter 3. We'll apply nodal analysis to find out the relationship between the output and input. By looking at the inverting terminal, the V minus node, this is called an inverting terminal. We can write a nodal equation. So we count the current goes into the node is equal to the current leaving the node. The current goes into the node comes from these two branches. The first branch is a V1 minus V minus divided by R1. The current goes through this branch into this node, that is a VO minus V minus divided by R2. The summation of these two, that is equal to the current leaving in this node, which is also the current goes into the op-amp, which is I minus. So this is how we get the first equation. The second equation comes from the non-inverting terminal. If we look at the non-inverting terminal, there are three branches connected to this node, V plus node. So we write the equation, the current goes into this node through this branch is V2 minus V plus divided by R3. The current goes into this node through this branch, that is 0 minus V plus divided by R4. And over here we select this node as a reference node. the summation of these two current that is equal to the current leaving the node I plus. So that is how we get the second equation. Combining these two nodal equations with the conclusion from ideal opamp model, we will be able to find the output and input relationship. So if we look closely, we notice that the VO is a linear combination of V1 and V2. The coefficient for V1 is a negative number. The coefficient of V1 is a negative number, and this depends on the ratio of R to R1. So by looking over here, the reason that it has a negative sign because it's connected to the inverting terminal, and there are two resistors connected over there. The coefficient depends on the resistors, and the coefficient for V2 is positive. V2 is connected to the non-inverting terminal. That is why it's positive, and the coefficient for that depends on all these resistors. Let's look at a special case. If R4 is equal to R2 and R3 is equal to R1, look at over here. R1, R2, no, R4 and R2 are the same, and R1, R3 are the same. So if we do that, we find that VO is equal to R2 over R1 times V2 minus V1. We can select resistors to meet a certain requirement that will allow us to design circuits of certain functions. For example, if I ask you to design a circuit that will be equal to some relationship of something times V2 minus something times V1, you will know this will be a good template to start with. But at the same time, because this template have multiple different resistors, so you have a lot of choices to select resistors.